Hey everyone. It's been a little while since I've done a video for you, especially one not over Khan Academy, but there's not really a good Khan section or anything I found online that really helps you figure out what these logarithm things are. So I'm going to take you through a couple problems that I've made up and see if we can kind of maybe make some sense out of them. So hopefully by this point you've gone through the Khan Academy sections I did assign, the first three where you started building exponential equations and looking at how those are set up. If you haven't done that, you should definitely pause this video or stop the video and go back and work out those Khan Academy sections, because I'm going to kind of assume that you already know how to do that. So each of those equations has a general formula where you have some starting amount and then you multiply it by some rate to an exponent. So our x is in the exponent this time. And that's what makes these things grow exponentially. All their graphs, if you ever graph one, look something like this, where it kind of starts slow, but then it speeds up and speeds up and speeds up and gets steeper and steeper and steeper. So it's growing faster and faster and faster. That's the idea of exponential growth. Retirement accounts work this way. A lot of savings account kind of banking investments. Populations tend to work this way, where you've only got a couple people making babies, not going to make much effect. But as those people make babies, they make babies, and make babies, and make babies, and make babies, it expands out more and more and more and more. It's not a straight growth like what's called linear. These are exponential, where it starts slow and then speeds up and speeds up and speeds up very fast. So, anyways, the way we started out is the world population in 2000 was about 6.08 billion. So that sounds like our starting amount. So we're going to have y equals 6.08, and we're going to multiply that by some rate. Now, this is where our percent work from last chapter starts coming in, is that we need to grow 1.26%. So we have 100% is what we had before. Having 100% of something isn't going up or down any. It just means you have what you have. It stays the same. So if we want it to grow, we need to add on 1.26%. So that will give you 101.26%. Right? So that's the amount it's growing by. But you don't really want to use the percent number. What you want to do is move your decimal over two places so that we can drop that percent sign off. Because what percent means is per 100. Like cent is in like century, or cents in a dollar is 100. Excuse me. So per 100, when you divide by 100, it moves your decimal left two. So we would use the number 1.0126. That is our growth rate. If you multiply something by that decimal, each time the answer you get back will be 1.26% larger than it started out as. And so we put an X up there saying that that's going to happen over and over and over and over and over and over again. It's going to grow by that amount each year, so it's going to continue happening. We're going to keep multiplying by that thing. So that's the equation. And you could see real quick, if I wanted to show that we have 6.08 billion, and we're going to multiply that by 1.0126. So I get something a little bit larger, just still over 6 billion, 6.15, a little bit bigger than before. Oh, I have to times it again. Sorry. Times by 1.0126. Again, grows a little bit more, 6.23 billion. Times by 1.0126. 6.3 billion. So it's going to take a while before it really starts increasing. And I want to know how long until it gets to 20 billion. Could you imagine doing this over and over and over again until you get to 20? Like, that's going to take forever. So we have this thing called logarithms that help us solve for a specific output. If I have 20 is what I want my population to get to, and I use my equation, my starting amount times my rate, man, what I can do is divide this front number off. So I'm basically solving for x here. You divide off your front number. So 20 divided by 6.0, we'll round that to 29. Right, the 9 here would round that 8 up to a 9. So 3.29 I'll use some squiggly equals because I rounded. 1.0126 to the x. So here's the big trick. What a logarithm is. Just the way that your calculator has add, subtract, multiply, and divide buttons, it also has a log button. So logs, what they're doing is they're exponenting. Like if you're doing an exponent, you're multiplying something over and over again, the logarithm works backwards. It's kind of like how squaring, right? Squaring is a specific exponent. It's a 2 exponent. And square rooting are opposites. When you have a variable up in your exponent, logarithms undo that. They take it apart for you. It's kind of more complicated than that, but I'm trying to keep this chapter simple since a lot of you are virtual. So what we can do is just the way that like we divided on both sides, we're going to log both sides. So I just put a little word log there next to each of those, and you'd rewrite that as log 3.29 equals log 1.0126 to the x. So I logged both sides. And usually you can skip writing this step because the whole reason we bring logarithms into this mix is that there's a property that says logarithms with an exponent are the same thing as if you multiply that exponent times the logarithm. Or in other words, you can just drop your exponent down. So now we have the x out of the exponent, right? The whole idea we're trying to do here is solve for how much time it will take to reach 20 billion. And so to do that, I need to get that x by itself. Well, when it's tied up in the exponent, that's really tricky to do. If we bring it down like this, now all I have to do is divide. Let me show you. 3.29. It's the same over here. And then I can divide by the log that's left over. Because as crazy as that looks, it's just a number. I'll spare you the details of what the number means. But yeah, if it's being multiplied by our x, we just divide by all that crazy looking junk. And this, as crazy as it looks, is what you type into your calculator to get your answer. So we're going to you hit the log button. If you're working on Desmos, I'll show that on the next example, what you can do on Desmos. So if you have a graphing calculator, or actually your iPhone has the function as well if you turn it sideways, log, the iPhone's kind of tricky though, I wouldn't recommend it. Log 3.29, close parenthesis, divided by log 1.0126, close parenthesis, enter. Woo! 95 years, just over 95 years, 95.1 years. So it would take just over 95 years before our 6.08 billion reaches 20 billion. And it kind of makes sense because 1% growth isn't very much, right? It's a pretty slow growth rate. But again, it's this whole idea that it takes a lot of time to do anything right away. But then after a while, it's like, woo, skyrockets. It takes off. That's the whole idea of exponential growth. So maybe see if you can pause the video and work ahead if you'd like to. But I'm going to pause real quick so that I can pull up Desmos and show you how to do the next one with Desmos. All right. So I started the video only with the DocCam version on. So I've put my laptop under the DocCam rather than starting a whole new video. Just real cool to play around with this right now before I actually show you the Desmos thing. All right, sorry. Hopefully this works. Yell at me if it doesn't. But on Desmos, if we wanted to solve that same problem, what you do is you just come over here and you can use next to the shift button, there's the question mark with a slash. If you push that, it makes a fraction. And you can just straight up type the word log. And then the thing that we wanted to do logarithm was 3.29, and then down below log 1.0126. And you can see we get the same answer right there, the 95.1. So hopefully you can see this. I can't really check. I mean, if I click back over, it'll go away, and I can't see. I can see it there. Cool. So Yes, that is how you can use Desmos if you don't have a graphing calculator at home. Again, I would not recommend using the iPhone because the order of operations is a little bit different in the way you type it in. So just that being said, I'm going to put this back aside and just use the graphing calculator. Just know that you can use Desmos to solve these problems as well. So I'm going to pause how I move stuff around. That's all right, so I'm going to speed this up a little bit because this video is getting really long. So a computer's value starts at this amount and it depreciates, which means it goes down. It decreases by 14.3% per year. So first thing is you always want to use the percentage you have left whenever you're using these equations because we don't want it to tell us how much we've lost. We want the equation to tell us how much value is remaining. So what you have to do first off is take your 100% and take away 14.3% to find what percent left you have each year. So 100 minus 14.3 gives you 85.7. So we're going to use that number, 85.7, in our equation. And again, remember, you want to drop your decimal left 2 places. That way we don't have to use the percent sign over here, just like what we did back up here. I had 101.26%, but if I move my decimal over 2 places, then I don't have to use the percent sign anymore, and it makes the calculations easier. So we start with 6,500, and we're going to have 0.857 to the x. That's the equation. As a rule of thumb, you're going to have numbers smaller than 1 when it's going down, and numbers bigger than 1 when it's going up. So if you had a graph of something like this, it would actually look like this right here, where it drops really fast, but then it kind of levels out. So it's almost the opposite effect. You drop a lot right away, but then it kind of slows down. So this would be called exponential decay, and this is exponential growth. All right. Now to solve how much until it's only worth $100, 6,500 times 0.857 to the x. So to solve this out, you're going to divide both sides by 6,500. Get rid of that front number first. Let's keep a couple decimal points since this is such a small decimal. 0.0153. 0.0153 equals 0.857 to the x. And here's where now you can use logarithms on both sides. And in doing that, it allows you to drop your x down. So I'll have log of 0.0153 equal to x times log of 0.857. All right, I know it's super technical work. This is some of the most technical stuff we'll do all year, so hang in there. I promise you I've scaled this back from what it was supposed to be. The normal Algebra 2, if we had been in person kind of work, is crazy with logarithms. But this is just so that you can find input values that give you specific output values. It's honestly the most useful thing that we can possibly do with logarithms. And even this is pretty questionable. So log 1.0, oh no, not 1.0153 divided by log 0.857. 27.1-ish. Yeah, if I round, 27.1. So if I start with a computer at $6,500, that's a pretty expensive computer. It's going to take a long time before it only has a worth of $100, right? It takes quite a while before it gets all the way down to 27. Even though it's losing a pretty big chunk of its percentage, again, it's going to drop down to maybe like $500 pretty quick. But then you can see how it kind of levels off. To get from like maybe 500 to 100 takes quite a bit longer. So, and same thing kind of happens with like new cars, right? Like as soon as you drive a new car off the lot, you lose a lot of its value because it's not new any longer. But then, you know, the difference between a 10-year-old and 12-year-old car isn't really as big of a deal as a brand new car and 2-year-old car, right? So that's the idea, that it drops a lot and then it kind of doesn't really matter that much anymore. So, Okay, you should definitely try to pause now because I'm just going to put the answers up to the rest of these and talk through them to try to get this video wrapped up. But I at least want to give you a little bit more guidance on how to finish these out. So see if you can pause and do numbers 3, 4, 5, and 6 on your own. All right, so here's me setting up the exponential for number 3. We started with 80. And again, it's decreasing, so I subtracted 3.5 from 100, and I have 96.5. Oops, put my decimal in the wrong place there. 0.965. Because after I get the 96.5%, I have to move my decimal left 2 places so that I can get rid of the percent sign. From there, I set it equal to 3. Divide by 80, log both sides, and divide by the logs to find that it would take 92 years before those 80 animals only have 2 animals left, or 3 animals left. So again, quite a bit of time, just like it was for the town growing up here, or the world's population growing. This is quite a while before it gets down to just 3. Baseball card starts at $50. You have a 3% growth. How long until that $50 card's worth $1,000? Well, again, you set it up as 50 times 1.03. This is the 100% plus an extra 3%. So 103% with the decimal moved left 2. Divide by the 50. Log both sides. Divide by the log. And you'll get 101 years. So maybe not trying to invest in baseball cards is the best way to plan for your retirement. You're probably gonna not make it that old. So maybe look at other things that have a better growth rate than baseball cards. Let's see. We start at $18,000 with our new car, and we're losing 25% each year. Now that's a little high for cars depreciating. Your car doesn't lose a quarter of its value every year. But for this problem, we can look at the idea that it's going down 25%, which means I have 75% left over. I want to know how long until my $18,000 car is only worth $5,000. If you divide by 18, log both sides, and divide by your logarithm, you get 4.4 years, which again, that's a really, really high percentage rate. So that's not really reflective of reality. I should change that. But that is how you would solve the problem as it is set up. You invest $75,000 at a rate of 12.5% per year. So again, we have 1 point because it's 112.5. Right, when I set this up, it's 100% plus because it's growing, it's increasing. So I get 112.5, and then I move my decimal left 2, so 1.125. From there, I divide by the 75,000, log both sides so I can drop my exponent, and then divide by the logarithm to get about 41.5 years. All right. Down here are the same problems, or the same. I mean, they use logarithms, right? All these have the variable and the exponent, but as you can see, the way that I work these out, some of them have extra junk up here in the top. So after I log both sides and drop that stuff down, I divide off the log like we were doing before, and then I finish solving for x. So here, once I divided the logs and got 3.11, I subtract that 1 to finish getting the x by itself. So that's the only thing I wanted to point out is that's kind of an extra little bit. There'll be some more of those on your review. And if you haven't worked these out already, again, you should pause and then just come back to the video and check your work with mine. But it solves very similar to those up there. You're just trying to get x by itself. So you're going to use logarithms to drop your exponent. If there's something out front, get rid of that first and then log. And you can throw out 11 and 12. I was going to show you how to go in the reverse order, going from logs back to exponential stuff, but it was taking up too much time in class, so I wanted to cut that part out. We're just using logs to solve exponential equations is all we're doing here. So, sorry that was a long video, guys, but hopefully it's helpful. We spent about a week doing this in class. So spend some serious time working on it. Email me with questions. This is the core of your quiz. When you get to the review, it looks just like your quiz will, and it is mostly problems like this up here. So really spend some time between this and the review, making sure you understand how these problems work, and send me screenshots of problems you don't understand, or take pictures, or just email me saying, I don't get it. Whatever you got to do, let me know. I'm here to help.